Something is sitting at the center of a distant galaxy that should not exist. Not by the rules we thought we understood. A black hole so massive, so fully formed, that the universe itself barely had time to build it. And yet, there it is. Measured. Confirmed. Waiting for an explanation that our current models struggle to provide. To understand why this matters, you need to appreciate what a supermassive black hole actually is. These are objects containing millions, sometimes billions, of solar masses, compressed into a region of space where gravity curves so severely that not even light can find a way out. The boundary where escape becomes impossible is called the event horizon. Cross it, and general relativity tells us there is no locally detectable change in that moment. No wall, no flash, no signal. Just the quiet, irreversible end of any path leading outward. At the center, theory predicts a singularity, a point where the curvature of space-time becomes mathematically infinite. Whether that singularity is physically real, or whether it marks the edge of what our equations can honestly describe, remains an open question. There is consensus among astronomers that supermassive black holes occupy the centers of most large galaxies. Our own Milky Way hosts one, the radio source known as Sagittarius A star, whose mass has been measured at approximately 4.3 million times that of the Sun, determined by tracking the orbital motions of stars moving around it. That measurement method, watching stars curve through space around an invisible gravitational anchor, is one of the most direct tools we have. It requires no assumptions about light or radiation. The orbits themselves are the evidence. But Sagittarius A star is, in cosmic terms, a modest object. The black holes that challenge our models are found not nearby, but at extreme distances, meaning we observe them not as they are today, but as they were billions of years ago when the universe was young. And some of them are enormous, billions of solar masses, fully assembled, shining as quasars, among the most luminous objects the universe produces, powered by accretion disks of infalling plasma, heated by friction to temperatures that radiate across the observable cosmos. Here is where expectation and observation diverge. Black holes grow by absorbing mass from their surroundings. That process takes time. Matter must fall in, heat up, radiate away excess energy, and finally cross the event horizon. There are physical limits on how quickly this can happen. Limits tied to the pressure of the radiation the infalling matter itself produces, which pushes back against further accretion. Standard models of black hole growth, built on these physical constraints, predict that assembling a black hole of several billion solar masses should require a substantial fraction of cosmic history. Billions of years of steady feeding. The problem is that we observe quasars powered by black holes of that scale at redshifts corresponding to epochs when the universe was less than 1 billion years old. The universe did not have enough time, under standard growth assumptions, to build what we are seeing. The black hole grew too fast. Or it started from something much larger than a single stellar collapse. Or both. This is not a marginal discrepancy. It is a structural tension between the observed population of early, massive black holes and the physical pathways our models allow. How do we know what we know here? The instruments involved span decades of observation. Quasars are identified through their extraordinary luminosity and characteristic spectral signatures. Their distances are inferred from redshift, the stretching of light as the universe expands, which shifts spectral lines toward longer wavelengths in a measurable, well-calibrated way. Black hole masses in quasars are estimated through methods including the width of emission lines in the quasar spectrum, which reflects the velocity of gas orbiting the black hole. These are indirect measurements, and they carry meaningful uncertainty. Mass estimates derived from emission line widths depend on geometric assumptions about how the emitting gas is distributed and moving. Different calibrations can shift the inferred mass. The uncertainty on any individual quasar mass can span a factor of a few in either direction. That uncertainty matters when evaluating the severity of the problem. If mass estimates are systematically biased high, some of the tension relaxes. But the population of high redshift, high-mass quasars is large enough, and the measurements consistent enough across independent methods that the core challenge does not dissolve under reasonable error bars. Something genuinely unusual happened in the early universe to produce these objects. Several hypotheses compete for the leading explanation, and they are not mutually exclusive. One possibility involves the direct collapse of massive gas clouds in the early universe, bypassing the ordinary stellar life cycle entirely and forming what theorists call direct collapse black holes, seeds already far more massive than anything a single dying star could produce. Another pathway involves the runaway merging of stars in dense early clusters, building an extraordinarily massive star that then collapses into a heavier than usual seed. A third involves sustained super-Eddington accretion, growth rates that exceed the standard radiation pressure limit, possible under specific geometric or radiative conditions where much of the radiation is trapped and advected inward rather than escaping to push back against infalling matter. Each of these mechanisms is theoretically plausible. None has been directly observed in the act of producing a black hole seed. The direct collapse scenario requires specific conditions: metal-poor gas, suppressed cooling, intense radiation environments that may have existed in pockets of the early universe but are difficult to confirm observationally at those distances and epochs. Super-Eddington accretion has some indirect observational support from certain classes of ultraluminous X-ray sources in nearby galaxies. But whether early quasars grew this way remains a hypothesis rather than a confirmed mechanism. The best current explanation, ranked by the weight of available evidence, is probably a combination: heavier than stellar seeds formed through direct collapse or dense cluster dynamics, followed by episodes of rapid, possibly super-Eddington accretion during the gas-rich conditions of the early universe. No single mechanism appears sufficient on its own to explain the full observed population. The problem likely has more than one solution operating in different environments. What would change this picture decisively? Direct detection of black hole seeds in the process of formation. Intermediate mass objects at high redshift, caught before they have grown into the billion solar mass giants we observe as quasars. Next-generation observatories operating across infrared and X-ray wavelengths are designed with exactly this capability in mind. Finding a statistical population of massive seeds at redshifts beyond the known quasars would strongly support the direct collapse or dense cluster pathways. Finding none, despite sufficient sensitivity, would force a harder look at super-Eddington growth from smaller seeds. Either result would sharpen the theory considerably. What the evidence has already changed is our picture of cosmic history in its earliest chapters. The universe was not a slow, orderly place where structures assembled patiently over billions of years. In its first few 100 million years, something was already building objects of staggering scale. Concentrations of mass that would anchor galaxies, drive feedback across enormous volumes of space, and shine with a luminosity that we can still detect across nearly the entire observable universe. The black hole that grew too fast is not an anomaly to be explained away. It is a signal that the early universe operated under conditions and through pathways that we are still working to understand. And that question, what the very first black holes looked like, how they formed, and what they seeded, connects directly to the next frontier. Whether the structures we see today, the galaxies, the clusters, the cosmic web itself, carry in their architecture the fingerprints of those first, impossibly fast beginnings.